Okay, so today's task is um, this one, 2385, amount of time for binary tree to be infected. So let me do this one. So I solved this task couple minutes ago. Um, it was a quite new task for myself. Um, yeah, struggled a little bit. Um, but let me record this attempt and I'll try to explain my approach. So speaking about this problem, so basically the authors of this problem uh, give me this binary tree, and one of these nodes of the binary tree is infected, and this infection spreads to adjacent nodes. So in case of this, in 1 second, the infection gonna spread to nodes 1, 10, and 6. In 2 seconds, the infection gonna spread to node 5. In 3 seconds to node 4. In 4 seconds to node 9 and 2. So the output here shows so what the question is for this task. Return the minimal time required to infect all the tree. If the root is given and if the infection start value for the node is given. So they asked to go um, and find and convert this binary tree to the graph and do traversal. Like I can do that like B, BFS traversal and do that like how many will we reach all the nodes, and if we do one step from one hop from the node from the start node, from the start vertex, and then two, and then three, and then gradually expand it using BFS, and then until all the nodes are visited, all the vertices are visited in the graph, and the minimal time to reach all the vertices in graph, if I start at 3, gonna be the output. But this approach is quite verbose. I have to go through the binary tree, save it to the graph. I'll have to do all this manipulations, and to me it sounded like really like time consuming, and also might be not very efficient in terms of like space. I need to save the graph, so the space complexity gonna be of n, whereas n number of nodes. I need to traverse the graph again, go through the graph, have this um, visited array probably, or like linked list, and like again it's often time complexity. So what I want to do is to solve this with O of one space complexity and of an time complexity. So what my plan is. So my plan is to have a recursion starting from the root, and then there are two options available. Either we have a start node as one of the children nodes, or we don't. Let's say if we go to left, so 1 has a start node in this case. 1 has 3 as a start node as one of its children, direct right child, and 5 doesn't have start nodes as a children. So there are like two cases. Either children have children or sub3 has a start node among its nodes, or don't or not. And in case it doesn't have start nodes, I just wanna percolate the maximum that we have for the left and right subtree. In case if it does have a start node, um, I wanna kind of have two variables. The first one will be the distance from my leaf to the start node, and the second variable gonna be the distance from the start node to the current one. And then every time I will percolate the start node up, I will do this check if there are any if there is a star tree among the children, and if yes, I need to kind of compare what the distance between the let's say in this case between the left subtree and the start node, and what's the distance between the, let's say, left and right children or subtrees to the start node, and compare them. If the one is bigger than another, like if this like path is bigger than the like either this or this, pass to 10, from 3 to 10, or from 3 to 6. If it's bigger, in this case it's bigger, so I need to just put this path distance as a distance, like substitute this path distance as like here we have one distance, but I will just pass to start node. I will substitute like 1, 2, 3, 4. Instead of 1, I'll put 4 here, and then the path from the start node to the parent one will be incremented by 1. Yeah, so that's the idea is, and I'll have the kind of private class just for storing this information. Pair class pair, and then I'll have the boolean flag has start, so it will be equal to false initially by default. And then I'll have the two variables. Let's say we have public. I'll wanna make my life a little bit easier. Public distance from parent to start, from P to S, distance parent P to S to start, and then public distance leaf to start. And it's gonna be 0, and then I'm gonna have this public constructor where int distance parent to start, parent to start, and then this okay, and I'll have this private pair DFS, and I'll put the tree node there, node, and then int start. So if node equals null, I'm gonna just return new pair with a -1 distance. So it means that whenever we're gonna go like next to the parent, to the node that's a child to 10, I don't want to check like additional nulls and check if I'm gonna go there or not, if it's null or not. And in order, like if I'm gonna go there, to the null, I'll just return distance -1. So next time this distance will be reflected. So I'll add -1. So the distance from 10 to 3 gonna be 1. I'm gonna just add, so -1 plus 1. So this distance gonna have 0, and then it'll start from 0 up to the from 10 to 3 gonna be distance 1. Yeah. So if then I wanna do this pair right leaf right say right pair equals say left pair equals DFS node dot left and then start, and then pair right pair equals DFS node dot right, and then start. So let me explain the situation what I'm gonna do here. So I'll have this tree uh, and let's assume we go DFS. So we go DFS from left, we go right, we go left, and I go here to the null, and I return what here? I return pair with, let's say, pair distance here, distance to start. It's yeah, it's interesting naming, but distance to start is gonna be -1, and then distance start to parent gonna be equal. Let me just edit another, just for understanding. I can optimize it further. So I'll have this distance to start, distance lift to start, and then I'll have public distance leave to parent. So in case has start is equal true, these two variables gonna be used, and in case has start equals false, this variable gonna be used. And here distance start start to parent. So in this case, I'm gonna, in case I go to the null here, I'll return a distance a leaf to parent L to P. Yeah, gonna be equal -1 distance leaf to start gonna be a 0, distance leaf to start to parent gonna be 0, but I'm gonna ignore it because I don't have like right here I don't have like start node. I don't have start node as a parent for this subtree. So just go distance left to parent equals -1, and I'm gonna return this back to 9. So 9, I'm gonna go also to the right subtree, and then I'm gonna go distance left to parent, gonna be also -1, and I'm gonna have like um, two subtrees that are basically null, and it's gonna check what to use it. Um, uh, it will have it will choose the maximum among both of them, and maximum gonna be -1. So it will create a new pair with the distance left to parent equals 1 plus whatever maximum from node left and node right. So this case is gonna be distance left to pair equals 1. Equals 0. So I'll add -1, I'll add +1, and gonna be 0 this case, and equals 0. And I'll push this pair back to 4. 4 will do the same for the 2. It will go back to the null level. Oh, yeah, do go back to the with the -1 distance left to parent equals -1, and then I'll percolate it to the top, distance left to parent gonna be equals 0, and then with the 4 we'll choose the maximum we have here, so it percolate back distance left to leaf to parent equals 1, because 1 plus 0 gonna be 1, and then it will percolate the distance, the 5 will receive this distance left to parent equal 1. It will so here we'll percolate it with the distance left to so at 4 it's gonna be distance left to parent leaf to parent gonna be 1, and then the 4 will percolate it with distance left leaf to parent equals 2, and then 5 will percolated back with distance left leaf to parent equals 3. So if I go to the right subtree here, here is the trick. So I go down. So here I'm gonna have the same distance leaf to parent equals 0. Here is distance left leaf to parent equals 0. Then I'll calculate here distance leaf to parent gonna be 1. And because it's a start node, I will start using this other two variables, distance start uh, uh, to parent, and then distance leaf to start. So here I will do the following. Because this one is a start node, I will change the I will move the kind of what I'll choose the whatever we have the maximum here, and I'll percolate the following structure. Distance left leaf to parent gonna be equal 0, and it means that we don't use it anymore. Then I'll have this uh, different color, and then what I'll do, I'll save this has start flag equals true, and then I'll have distance start to leaf to start equals, I will take the distance leaf to parent, I will add 1. Oh no, I will keep it 1, and then I'll do the following: distance start to parent gonna be equal 1, and from now on I will increment this one in case this distance is kind of in case, I'll show you what will happen here. Um, so I'll percolate it back to 1, and at 1 we have like situation, very interesting situation. The left subtree uh, returned the following structure. So it returned distance leaf to parent equals 3, and then has start equals false. This subtree for the 1, what it returned the following. Has start equals true, and distance left leaf to start equals 1. Distance, so it returns like here it returns initial, it returns distance start to parent equals 0. And this leaf needs to decide what how to merge this information into single pair at 1. So this is a big question mark. So what I will recommend is to calculate the distance to the start from the left subtree. So it's gonna be like, let me change the color again. So it's gonna be like what the distance to the start, like if we follow through this path, what's the maximum distance, and what's the distance if we follow this path to start. So this distance is gonna be like this. It's gonna be the distance for this tree leaf to parent, so it's like 2 plus 1 here plus 1 here and plus for this subtree plus distance start to parent. In this case it was 0, so it's gonna be 2 plus 1 plus 1 plus 0, so it's gonna be 4. And this distance is gonna be just distance start leaf to start, and gonna be just 1. So in this case, the left path 1, it's longer. So what I'll do in this case, so I'll just substitute, I'll just move this distance to the kind of, so I'll remove this information, I'll break this information, and I'll say there is a kind of node, and the distance leaf to start gonna be equal 4, and then I'll use it in all following kind of in case we have like a parent to the 1, but in this case we don't have. So I'll have this following structure as a merged one. Pair at 0 gonna be the following. Has start equals true, then distance leaf to start equals 4, then distance start to parent gonna be whatever we had, 0 plus 1, so 1, and then I'll return it back. And in the final output I'll have this pair as a result, and I'll need to just return maximum between distance left to start and distance start to parent. And in this case I'll return 4 because this path is longer than this path, and we ended right here at 1. And we'll always have this has start at the root equals true, because it's guaranteed we have a start point somewhere either in the left subtree from the root or right subtree from the root. So this is a sketch for the solution. Let me start implementing that. So I'll simplify it: start to parent, then I'll have lift to start, and then I have lift to parent, and then lift to start to parent, L to P, and then I'll have a lift to parent equals L to P equals L to P, something like this. So I'll have this one, and I'll check in this case if L pair has start, if they both don't have start equals has start flag equals true, R pair has start, then I'll do the following. I'll do return new pair, and then distance L to pair gonna be max L pair distance L to P, and then R pair distance leave to parent, and then I'll add one here. Else either left pair or right pair will have a children, will have a has a start, and then I need to check also. I need to check, let's say, pair P equals new pair, and then I need to check if node dot value equals start, then pair that has start gonna be equal true, and then I'll do this distance leave to start gonna be, say, something like this. Distance leave to start gonna be distance, and then yeah, something like this, and then let's say we have public and then pair has start gonna be true, else I'm gonna have P distance leave to parent gonna be equal distance, and I'm gonna return this pair. In case we have either has start equals true for the left or right pair, I'll do the following. If let's say I'll consider this example first. So in this example, for the one we have R pair equals has start equals true. If equals true, I'll do the following. I'll do L if, so I have this let's say let int left distance to start, is gonna be equal left pair distance leave to parent plus 1, because it was for this, so we need to add this edge distance, plus 1 plus right pair distance um, start to parent int, and then int right distance leave to start, and then right distance it means like maximum distance in case we have like a shorter distance from the left subtree, then from the right subtree you're gonna save the maximum right subtree distance right distance lift to start equals r pair distance leave to start plus 1. So in case left distance gonna be greater than right distance to start, I'm gonna so I'll create a pair p equals new pair, and then case its left distance is greater than right distance to start, I'll do the following. I'll save pair dot distance leave to start gonna be equal left, and then pair distance start to parent gonna be 1 plus left left pair distance start to parent, and then pair has start equals true. So this is gonna be common, because if any children subtrees are gonna have has start equals true, then the bigger subtree that has it I'm gonna also have has start true. And in case otherwise, I'm gonna reuse the same p distance left leave to start equals right. No, I don't need to add it here plus 1. I don't need this plus 1 because it doesn't increase as you move further. And then pair distance start to distance start to parent gonna be the same. So this one can also be moved out. Yep, that's it, and then I'll do the following. I'll need to symmetrically copy this code and re-implement it again. And in the end, I need to return this result pair. So in this case, we have distance if this has start equals true is on the left, actually subtree, not like this on the right subtree. So we have right so right distance to start, distance leave to start gonna be r pair distance leave to parent plus 1 plus 1 plus l pair distance start to pair, and the left distance leave to start gonna be l pair distance leave to start, and then if right pair right distance left to start gonna be greater than left distance leave to start, I'm gonna save the parent pair distance leave to start equals this one, else uh, this one. Something like this, and this is gonna be the um, there in their output. I'm gonna have pair p equals dfs root start, and then return mass maximum pair distance start to parent, and then pair distance no distance yeah leave to start to parent. I need to double think about this problem, so like I always merge it. I wonder if I can just use distance left to start instead of this confusing distance start to parent. Okay, that's it. Let me sketch the. So this is a solution. So we have additional class as a pair, and it can be in two mode, depending on whether has start is true or false. This is a result of the call of DFS for the left or right subtree, and the left or right subtree can have can possibly have a start node, or it it can possibly it it might not have the start node, and in case it has a start node, I'll use this leaf to start and then start to parent variables, and in case it doesn't have a start node, it will have just distance leave to parent variable used. and then I'll merge it and return. Let me check if that works. If there is any case. No, it will not work in so um, the counterexample here like this one. So we have let's say we have a leaf node 1, and then we have node 2, and then start will be equal to, and then it will mean that I will return this pair p equal has start equals 1 equals true, and then distance leaf to start equals 0, distance start to parent equals, so this equals 0, and I'll return it like on this when I'm gonna exit the recursion from 2 to 1. And this one node will do the following. So it will try to call this minus and will return for the left subtree. It will return pair equals has start equals false, distance leaf to parent equals -1, and it will do the following. So it will add -1 plus 1 plus 1 plus 0. So it's going to be distance 1, and it will compare, and it will return, eventually it will return pair. So that at root I'll return parent equal so here like 1 will be equal will be less, will be equal actually this pass. No, actually. Yeah, this pass is longer than this pass. So this pass was 0, this pass became like 1, and I will return back which one. So has start will be equal true, and then distance leave to start gonna be equal 1, and then distance leave to distance start to parent gonna be equal also 1. So yeah, I guess you can substitute it. Let's check. Okay, less efficient, but still memory. Better memory, but I wonder what is used here. Okay, I guess this is pretty similar one. So they do that first left and right subject reversal, and they kind of returning int. They play with minus, oh, like -1. Mm. Yeah, it's less data, less data is traveled back and forth, like just return count to start to and max length. Okay, so okay, whatever. I'm gonna wrap up. I feel in more than for 20 minutes, so I guess this is fail. Yeah, that's it. Managed to solve the problem, but spent a little bit more time than actually scheduled on like 20 minutes interview for the one problem. So the status for this video is fail.